In 1977, a radio telescope in Ohio picked up a signal from space. It lasted 72 seconds. The astronomer who noticed it in the data, reviewing the printout days after the observation, circled it with a red pen and wrote one word in the margin.
Wow.
The signal had the exact characteristic scientists had been predicting for decades as the signature of an intelligent transmission from another civilization. The right frequency, the right intensity, the right pattern of rise and fall as Earth's rotation carried the telescope through the beam. It came from the direction of the constellation Sagittarius, and it has never been detected again, not once in the 47 years since. Every telescope we have pointed at that region of the sky, every survey, every dedicated observation, every attempt to reproduce what the Big Ear telescope recorded on August 15, 1977, has returned silence. Just silence. And that silence is the subject of this video. Not the signal, though we will come back to it. The silence. The overwhelming, unbroken 70-year silence that surrounds that one anomalous 72 seconds like an ocean surrounds a single lit match. Because here is what you need to understand about that silence before anything else. It should not exist. By every calculation we can make, by every equation that describes the number of stars in the universe, the fraction of them with planets, the fraction of those planets in habitable zones, the probability of life arising where conditions are right, the probability of that life developing intelligence, the probability of that intelligence developing technology. The universe should be full of voices. Not one or two, not a handful of civilizations scattered across the galaxy. Full, crowded, loud with signals and transmissions and the electromagnetic signatures of technological species going about their business across the Milky Way. The math says we should not be alone, and yet, every direction we look, nothing. Every frequency we monitor, nothing. Every survey of every star system within our detection range, nothing. Silence so complete, so consistent, so unbroken across 7 decades of searching and listening and watching, that the silence itself has become the most important data point in the history of the search for life. Because silence, when it is this total and this persistent, is not an absence of information. It is information. It is telling us something. Something about the universe. Something about life. Something about what happens to civilizations that reach the point we have reached. Capable of sending signals, capable of receiving them, looking out at a galaxy of hundreds of billions of stars and finding, in every direction, no one looking back. The silence from space is the most important unsolved problem in science. And it should terrify you. Not in the way that danger terrifies you. Not in the way that a threat terrifies you. But in the quieter, deeper, more persistent way that a question terrifies you when you realize it has no comfortable answer. When every explanation you reach for turns out to be worse than the question itself. Tonight, we are going to follow that silence to every place it leads. We are going to look at every explanation scientists have offered, every theory, every hypothesis, every carefully constructed argument for why the universe might be this quiet, and we are going to see what each one implies. And at the end, we are going to sit with the conclusion that the silence delivers, whether we want it to or not. Something out there should have found us by now. It hasn't. And that fact, that simple, quiet, persistent fact, is one of the most unsettling things about the universe we live in. To understand why the silence is strange, you first have to understand what the universe looks like on paper. Start with the stars. The Milky Way contains somewhere between 200 and 400 billion stars. Most of them are red dwarfs, dim, patient, long-lived. Many of them, we now know, are orbited by planets. The Kepler Space Telescope, which spent 9 years surveying a small patch of the Milky Way and monitoring over 150,000 stars for the tiny dimming caused by a planet passing in front of them, found planets everywhere. Not occasionally, not in special circumstances. Everywhere. The best current estimates, extrapolated from the Kepler data and subsequent surveys, suggest that the average star in the Milky Way has at least one planet. Many have more. The total number of planets in our galaxy alone is estimated at somewhere between 100 billion and 1 trillion. 1 trillion planets. In one galaxy, and the observable universe contains approximately 2 trillion galaxies. The number of planets in the observable universe is not a number that has any intuitive meaning. It is somewhere in the range of 10 to the 24th power, a 1 followed by 24 zeros. A number so large that comparing it to anything in human experience produces comparisons that are themselves incomprehensible. Now ask, of those planets, how many are in the right place to support life? The habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface, is not a narrow sliver. For many stars, it is a reasonably wide band. And liquid water is not the only possible solvent for life, though it is the one we know works. The habitable zone concept, applied to the Milky Way alone, suggests somewhere between 10 and 40 billion Earth-sized planets in the habitable zones of Sun-like stars. Add in the red dwarfs, which are far more numerous and which also have habitable zones, though closer to the star, and the number climbs higher. Let's say, conservatively, that 1 in 1,000 stars in the Milky Way has a planet capable of supporting life as we understand it. That is 200 to 400 million potentially habitable planets in our galaxy alone. Now ask, on how many of those planets does life actually arise? This is where the uncertainty becomes significant. We do not know how easy or hard it is for life to begin. We know it began on Earth, and we know it began relatively quickly by geological standards, within a few hundred million years of the planet's surface cooling enough to support liquid water. That suggests to some scientists that life may arise readily wherever conditions permit, that it is not a miraculous accident but an almost inevitable consequence of the right chemistry in the right environment. Others disagree. They argue that the origin of life, the specific series of chemical events that produced the first self-replicating molecule, the first cell, the first system capable of Darwinian evolution, may be extraordinarily unlikely. That the fact that it happened on Earth tells us nothing about how often it happens elsewhere because we are, by definition, only able to observe a universe in which it happened at least once. This is called the anthropic selection effect, and it is one of the murkiest philosophical waters in all of science. But even if we apply a very conservative number, even if we say that life arises on only 1 in a million habitable planets, we are still left with hundreds of potentially life-bearing worlds in the Milky Way. And life-bearing does not mean intelligent life. It means life of any kind: bacteria, slime, the microscopic, the simple, the ancient. For intelligent life, for life that develops technology and communication and the ability to wonder about the stars, the number drops further, maybe much further. Intelligence seems, from the only example we have, to require billions of years of evolution. It requires complex multicellular life. It requires something analogous to nervous systems and brains. The path from the first bacterium to Homo sapiens took approximately 3.8 billion years, and it was not a straight line. But even with all those filters, even being maximally conservative at every step of the calculation, the numbers remain stubbornly large. In 1961, an astronomer named Frank Drake formalized this reasoning into an equation. The Drake equation. You may have encountered it. It is one of the most famous equations in science, not because it gives a precise answer, it doesn't, but because it organizes the question. It takes the number of stars in the galaxy and multiplies it by a series of fractions. The fraction with planets, the fraction of those with habitable planets, the fraction of those where life arises, the fraction where intelligent life arises, the fraction where that intelligence develops detectable technology, and the length of time that technological civilization lasts. Plug in optimistic numbers and you get millions of civilizations in the Milky Way right now. Plug in pessimistic numbers and you get one, us. The equation's range is so wide, from 1 to millions, that its scientific value is debated. But here is what is not debated. The universe is 13.8 billion years old. Earth is 4.5 billion years old. The Milky Way has been forming stars for more than 12 billion years. Stars similar to the Sun, with similar planetary systems, have been orbiting the galaxy for billions of years longer than our Sun has existed. If life arose anywhere else in the Milky Way, If any civilization anywhere in our galaxy reached our level of technological development even 1,000,000 years before we did, they have had 1,000,000 years head start. 1,000,000 years. The Wright brothers flew at Kitty Hawk 120 years ago. Humans landed on the moon 55 years after that. We launched interstellar probes within living memory. Whatever a civilization with 1,000,000-year head start can do is not something we can easily imagine. But here is the minimum. At the minimum, they should have been capable of sending signals, radio waves, laser pulses, some form of electromagnetic communication across interstellar distances. Radio waves travel at the speed of light. A signal sent from a civilization on the other side of the Milky Way reaches us in about 100,000 years. If anyone out there has been transmitting for even a fraction of their 1,000,000-year head start, we should have detected something by now. We haven't. The numbers say we should not be alone. The sky says we are. That contradiction has a name. We have been listening, not casually, not occasionally, systematically, deliberately, with purpose and precision and dedicated scientific effort. For more than 70 years, humans have been pointing instruments at the sky and asking the same question. Is anyone out there? The formal search began in 1960 when an astronomer named Frank Drake, the same Frank Drake who would later write the equation, pointed the 26-meter radio telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia, at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, each about 11 light-years away, each potentially, just potentially, with planets, each close enough that a signal sent from there could have reached us within a human lifetime. He called the project Ozma, after the queen of the fictional land of Oz, a place far away, difficult to reach, populated by exotic beings. He listened for 2 months. Nothing, not a hint, not an anomaly, not a single data point that deviated from the expected background noise of the galaxy in a way that suggested intelligence. 2 months of careful listening to 2 carefully chosen targets, and the result was a flat line. It was a beginning, not a discouraging one. Exactly, 2 stars is a tiny sample and 2 months is a short time, but the shape of what was to come was already there in that first flat line. The search would continue. The instruments would improve. The number of stars surveyed would grow from 2 to thousands to millions. And the answer would remain, with one partial exception, the same. Nothing. SETI, the search for extraterrestrial intelligence, grew from Drake's first tentative project into a global enterprise. Dozens of programs across multiple decades and multiple countries, using radio telescopes ranging from modest to enormous, covering different frequency ranges and different regions of the sky, applying different search strategies and different signal processing techniques. The logic of searching at radio frequencies is straightforward. Radio waves travel at the speed of light. They can cross interstellar distances, even galactic distances, without being significantly attenuated by the interstellar medium. They require relatively modest technology to produce and detect. Any civilization that has reached the level of technological development we achieved in the mid-20th century should be capable of radio communication, both intentional and unintentional. We have been leaking radio signals into space since the early 20th century. Every television broadcast, every military radar pulse, every radio transmission, all of it traveling outward from Earth at the speed of light, forming an expanding sphere of electromagnetic noise roughly 100 to 120 light-years in diameter. A sphere that, if any civilization with a radio telescope exists within that radius, they could potentially detect. The logic goes both ways. If they are transmitting, we should be able to detect them. And even if they are not transmitting intentionally, even if they are simply going about their technological civilization without any specific effort to communicate, the ambient electromagnetic noise of their activity should be detectable, if they are close enough and if their technology produces signals powerful enough. We have heard nothing. The most significant dedicated SETI effort in history was Project Phoenix, which operated from 1995 to 2004 and used some of the largest radio telescopes on Earth, including the 305-meter Arecibo telescope in Puerto Rico, the largest single-dish radio telescope ever built, to survey more than 800 stars within 200 light-years of Earth. The search covered 1.2 to 3.0 gigahertz, a frequency range that includes what some scientists have called the cosmic watering hole, a range of frequencies relatively free of background noise, where a communicating civilization might logically choose to broadcast. 800 stars, 200 light years, 9 years, the most sensitive radio survey of nearby stars ever conducted. Silence, not a hint, not a candidate signal, not a single anomaly that required follow-up investigation because it might, just might, be something other than natural noise. Since Project Phoenix ended, the search has continued. The Allen Telescope Array in California, funded partly by Paul Allen of Microsoft, was built specifically for SETI and has surveyed millions of star systems. The Breakthrough Listen initiative, launched in 2015 with a $100 million commitment from Russian-Israeli investor Yuri Milner, is the largest and most comprehensive SETI program in history, using major radio telescopes to survey the 1 million nearest stars in the Milky Way, the 100 nearest galaxies, and the entire plane of the galaxy, at frequencies and sensitivities never before achieved. Breakthrough Listen has published results covering billions of radio signals analyzed and filtered. Among those billions, a small number of candidate signals have been identified, signals that initially appeared unusual, that were flagged for follow-up investigation, that required more analysis before being classified. Every single one was eventually explained as terrestrial interference, instrumental artifact, or natural astronomical phenomenon. Every single one. 70 years of systematic searching with improving technology and increasing sensitivity. Millions of stars surveyed. Billions of signal candidates analyzed. And the result is the same result Drake got pointing a 26-meter dish at 2 nearby stars in 1960. Silence. The only exception to this silence, the one data point in 70 years that genuinely gave scientists pause, happened in the summer of 1977, on a night in Ohio when a telescope called the Big Ear was conducting an automated sky survey. And it happened for exactly 72 seconds. The Big Ear telescope was not a conventional radio dish. It was a flat reflector, a large, flat aluminum surface on the ground, tilted slightly to reflect radio waves from the sky up toward a stationary receiver mounted above it. It was 340 meters long and 120 meters wide. Modest by the standards of dedicated radio astronomy. But it was reliable, and it had been running a sky survey for years when, on the night of August 15, 1977, it recorded something unusual. The signal appeared at 10:16 p.m. Eastern Standard Time. It came in at a frequency of 1,420.4556 megahertz, extraordinarily close to the emission frequency of neutral hydrogen, which is 1,420.4058 megahertz. The hydrogen line, the most abundant element in the universe, resonating at its natural frequency. A frequency that SETI researchers had identified, decades before the signal appeared, as the most logical choice for an interstellar communication attempt, because any civilization capable of radio astronomy would know it, and because its significance as the hydrogen line would be recognizable to anyone with sufficient understanding of physics. The signal was strong, very strong. It reached a signal-to-noise ratio of 30, meaning it was 30 times louder than the background noise of the galaxy at that frequency. In the context of radio astronomy and SETI, this was extraordinary. The threshold for a signal to be considered interesting is typically a signal-to-noise ratio of around 3. This was 10 times that. It also showed the correct signature of a signal coming from a fixed point in space rather than from a terrestrial source or from a moving object. As Earth's rotation carried the Big Ear past the source, the signal rose in intensity, peaked, and then fell, exactly as expected for a distant fixed source moving through the telescope's beam. The rise and fall followed the precise curve predicted by the telescope's geometry. The astronomer who found it in the data days later was Jerry Emin. He was reviewing computer printouts of the telescope's observations. The data was encoded as letters and numbers representing signal intensities. When he reached the column corresponding to that night's observation and saw the sequence, 6EQUJ5. In the coding system used by the Big Ear's computer, letters represented intensities above 9. A meant a signal-to-noise ratio of 10, B meant 11, and so on. The letter U, the peak of the sequence, represented a signal-to-noise ratio between 30 and 31. Jerry Emmons circled the 6-character sequence in red pen and wrote in the margin, "Wow." The name stuck, the WOW signal. In the days and weeks and months that followed, astronomers turned every available instrument toward the region of sky where the signal appeared to originate, a region near the Chi Sagittarii star group, toward the center of the galaxy. They listened, they waited, they scanned the same frequency with the same telescope and with other telescopes. Nothing. The WOW signal has never been detected again. Not by the Big Ear, which continued operating until 1997 when it was demolished to make way for a golf course, an ending that feels almost deliberate in its indignity. Not by the Arecibo telescope. Not by any of the dedicated SETI programs that have pointed instruments at that region of the sky in the 47 years since. One signal, one night, 72 seconds, and then silence. The explanations proposed for the WOW signal span a wide range. Some researchers believe it was a natural phenomenon, a hydrogen maser, a cloud of interstellar gas that had been energized into emitting at the hydrogen frequency. Others have proposed it was a signal from a human-made satellite or piece of space debris, though the geometry of the observation makes this difficult to reconcile with the data. In 2017, an astronomer named Antonio Paris proposed that the signal might have been caused by a comet, specifically comets 266P/Christensen or P/2008 Y2 Gibbs, which would have been in that region of sky in 1977, because comets release hydrogen gas from their nuclei that could potentially produce a strong emission at the hydrogen line. The comet hypothesis was tested. In 2016, Paris used a 10-meter radio telescope to observe comet 266P/Christensen at the hydrogen line frequency and reported detecting a signal. But other researchers contested his methodology and his results. The comet explanation has not been widely accepted by the SETI community. The WOW signal remains, officially, unexplained. And its most unsettling quality is not the signal itself. It is the silence around it. If the signal was an intelligent transmission, if someone was broadcasting from a point in the direction of Sagittarius at the hydrogen line frequency, with enough power to produce a signal-to-noise ratio of 30 in a modest telescope 25,000 light-years away, why have they not transmitted again? Either they transmitted once and stopped, or they are transmitting continuously but we have somehow failed to detect it in 47 years of looking. Or it was a natural phenomenon that we have not correctly identified. Or it was something we don't have a category for. None of these options is comfortable. The WOW signal sits in the literature like a splinter that no one can quite remove. Not large enough to be conclusive, not small enough to dismiss, permanent enough to return to every time the broader question of silence in the universe is raised. One 72-second flash in 70 years of listening. Everything else, silence. And the question that silence raises, the question that Enrico Fermi famously posed at a lunch in Los Alamos in 1950, before the search had even properly begun, is not simply why we haven't heard anything. It is why, given everything the math implies, that is even possible. In the summer of 1950, Enrico Fermi had lunch with several colleagues at the Los Alamos National Laboratory in New Mexico. Fermi was one of the most significant physicists of the 20th century, the architect of the first nuclear reactor, a key figure in the Manhattan Project, a Nobel laureate. He was known, among his colleagues, for what they called Fermi estimates, rapid, back-of-the-envelope calculations that could reduce an apparently complex question to an order-of-magnitude answer through a series of simple, reasonable assumptions. The conversation at lunch had drifted to a cartoon in the New Yorker magazine that showed aliens stealing New York City trash cans. The discussion moved from aliens to UFOs to the question of interstellar travel. And then Fermi, reportedly, laughed and asked a question. Where is everybody? The exact wording varies depending on who is recounting the story. Some remember it as, where are they? Others as, don't you ever wonder where everybody is? The precise phrasing has been debated by historians of science for decades. But the question was clear. If the galaxy is as old as it is, if the conditions for life and intelligence have existed for billions of years, If the technology required for interstellar travel or at least interstellar communication is achievable by a sufficiently advanced civilization, then the galaxy should, by now, show signs of that intelligence. We should have been visited. We should be receiving signals. We should, at minimum, be detecting the electromagnetic signatures of technological civilizations going about their business. Instead, nothing. The question was a Fermi estimate in the purest sense. A simple calculation: large number of stars times large probability of life times large age of universe equals many civilizations that should be detectable. Observed number of detectable civilizations: 0. These two things cannot both be correct. Something in the chain of reasoning is wrong. Either the assumptions are wrong, life is rarer than the math suggests, intelligence is rarer than the math suggests, technological civilizations are rarer than the math suggests, or the conclusion is wrong, and we are simply failing to detect something that is there. Or there is a third possibility, which is the one that has most occupied scientists and philosophers in the decades since Fermi's question. The civilizations existed, and something happened to them. This question, the apparent contradiction between the expected abundance of intelligent life and the observed absence of any evidence for it, has become known as the Fermi paradox. It was formalized and popularized by a physicist named Michael Hart in a 1975 paper, and expanded on by a large number of researchers across multiple disciplines in the decades since. It has generated books and conferences and dedicated journal articles and more proposed solutions than any other question in astrobiology. None of the proposed solutions has been accepted as correct. None of them has been ruled out. And the reason the Fermi paradox has retained its grip on scientific and popular imagination for more than 70 years is precisely because every proposed solution has implications, often deeply unsettling implications, that go well beyond the question of alien life. The Fermi paradox is not just a question about whether we are alone. It is a question about the nature and fate of intelligence itself, about whether the trajectory from simple life to complex life to technological civilization is a common one or an extraordinary one, about whether civilizations, once they arise, tend to survive or tend to end, and about what that means for us. For a civilization that has just, in the last few centuries, developed the technology to ask the question. The most important framework for thinking about the Fermi paradox was introduced in 1998 by philosopher Nick Bostrom and economist Robin Hanson. It has a name that is deceptively simple: the Great Filter. The Great Filter is a way of thinking about the Fermi paradox that cuts through the philosophical complexity and asks a simple, brutal question. If intelligent technological civilizations should be common, if the math works out the way the optimistic reading of the Drake equation suggests, and yet we see no evidence of any in the observable universe, then something must be filtering them out. Something must be preventing them from appearing, or from surviving long enough to be detectable, or from expanding and colonizing the galaxy in ways we would notice. Whatever that something is, wherever in the chain from dead matter to communicating civilization the filter operates, is what Robin Hanson called the Great Filter. And the most important question the Great Filter raises is not what it is. It is where it is. Because if the Great Filter is behind us, if it is something in the early stages of the development of life or intelligence that is extraordinarily rare, something that Earth somehow managed to get past but that most planets have not, then we might be one of the first intelligent species in the galaxy. Maybe the first. And the future, at least in principle, is open. There is no wall ahead. We got through the hard part. The galaxy is empty not because civilizations always end, but because they almost never begin. That would be extraordinary news. Frightening in its own way, the loneliness of it, the weight of being the first but not despairing. Not a verdict. But if the Great Filter is ahead of us, if the thing that eliminates civilizations is something in the future of any species that reaches our level of technological development, then we have not yet faced the hard part. We are approaching it. The silence of the galaxy is not the silence of an empty nursery. It is the silence of a graveyard. Every civilization that has reached this point, the point of radio telescopes and nuclear weapons and the ability to contemplate their own extinction, has gone quiet. Not because they stopped broadcasting, because they stopped existing. and we are next. This is the great filter in its most unsettling form. The question is, which side of the filter are we on? To think about this carefully, you need to consider each step in the development from dead matter to technological civilization as a potential filter. Each step that is extraordinarily unlikely, each step that almost never happens, is a candidate for the great filter. Step 1. The formation of a star with the right properties in the right type of galaxy. This seems to happen fairly readily. The galaxy is full of sun-like stars. Step 2. The formation of planets in habitable zones. Also seems to happen fairly readily. The Kepler data suggests this is common. Step 3. The origin of life, the transition from chemistry to biology, from inert molecules to self-replicating systems. This is genuinely unknown. It happened on Earth. We don't know how often it happens elsewhere. Step 4. The transition from simple prokaryotic life, bacteria-like, without a nucleus, to complex eukaryotic life, cells with nuclei. On Earth, this transition took approximately 2 billion years and appears to have happened exactly once, with all complex life descending from a single common ancestor of the first eukaryotic cell. This may be a significant filter. Step 5. The transition from single-celled life to multicellular life. On Earth, this happened multiple independent times, suggesting it may not be an extreme filter. But it still required the prior step. Step 6. The emergence of complex animal life with nervous systems, sense organs, and the precursors to intelligence. This required a long evolution of increasing complexity. Step 7. The emergence of technology-capable intelligence, of species with manipulative appendages, social structures, language, and the cognitive capacity to develop science and engineering. Step 8. The survival of a technological civilization long enough to become detectable, to achieve spaceflight or sustained radio transmission, or some other signature we could observe. Each of these steps could, in principle, be the great filter. And the terrifying logic of the great filter is this: the more good news we find about the abundance of the early steps, the more evidence we accumulate that life arises readily, that complex cells evolve commonly, that intelligence emerges often, the worse news it is for our future. Because if all those things are easy, if life and complexity and intelligence all arise freely throughout the galaxy, and yet the galaxy is still silent, then the filter must be ahead of us. It must be something that happens to civilizations after they reach our stage, after they develop technology, after they start listening for each other. Finding life on Mars would be the worst news in human history, not because life on Mars is bad, but because if life arose independently on Mars, if two planets in the same solar system under similar conditions both produced life, then the origin of life is clearly not the great filter. Clearly isn't rare, which means the filter is somewhere further along the chain, somewhere ahead of where we are. The silence of the galaxy is, in the great filter framework, a form of hope. The hope that the filter is behind us, that the reason no one else is out there is that we got through something extraordinarily rare, and we did it on Earth and no one else has managed it. But it is a grim kind of hope, a hope that depends on us being almost incomprehensibly lucky. And every day we look at the sky and hear nothing. Every day the silence continues. We remain unable to determine which side of the filter we are on. The simplest explanation for the silence is the one that requires the least imagination. We are alone. Not alone in the sense that life doesn't exist elsewhere. It might, in simple forms, in the oceans of Europa or the subsurface lakes of Enceladus or the organic chemistry of Titan. But alone in the sense that intelligence, technological, communicating, civilization-building intelligence, may be extraordinarily rare. Rare enough that in a galaxy of 200 to 400 billion stars, we are the only example. This hypothesis goes by several names. The Rare Earth Hypothesis, from a 2000 book by paleontologist Peter Ward and astronomer Joe Kirschvink, is the most fully developed version. Its argument is that the emergence of complex, intelligent life on Earth required such a specific and unlikely combination of circumstances that it is effectively unique in the galaxy, possibly in the observable universe. The list of conditions that make Earth unusual, according to this argument, is long. Earth orbits in the habitable zone of a star that is unusually stable for its type. Our Sun is a relatively quiet star with low variability in its energy output. Many stars, including many red dwarfs, are far more active, producing frequent powerful flares that could strip away the atmospheres of nearby planets and bombard their surfaces with lethal radiation. Earth has a large moon, disproportionately large relative to the size of the planet, the product of a collision between early Earth and a Mars-sized object billions of years ago. That moon stabilizes Earth's axial tilt. Without the moon's gravitational influence, Earth's axial tilt would vary chaotically over geological timescales, producing wild swings in climate that might have prevented the long periods of environmental stability required for complex life to evolve. Earth has plate tectonics, the movement of the crustal plates that drives volcanism, mountain building, and the carbon silicate cycle that regulates atmospheric carbon dioxide levels over millions of years, keeping the planet's temperature relatively stable despite changes in the sun's brightness. Many rocky planets may not have plate tectonics. It may require specific conditions of planetary size, composition, and internal heat that are not universal. Earth has Jupiter, the solar system's largest planet, sitting in the outer system with its enormous gravitational influence, acts as a shield, deflecting or capturing many of the comets and asteroids that would otherwise rain down on the inner solar system at a far higher rate. A planet without a Jupiter might face a more intense bombardment regime that could repeatedly sterilize the surface before complex life has time to develop. Each of these factors, taken individually, might not be decisive. But taken together, the stable star, the large moon, the plate tectonics, the gas giant shield, the specific chemical composition of the oceans, the timing of the great oxidation event that produced an oxygen atmosphere, the mass extinction events that cleared ecological space for new forms of complexity to evolve, the argument is that Earth is not a typical habitable planet. It is an extraordinarily unusual one. And the emergence of intelligence on Earth required not just a habitable planet, but this specific chain of events, this specific sequence of catastrophes and lucky breaks and evolutionary experiments over 3.8 billion years. The probability of that exact sequence occurring is, the rare Earth argument suggests, extraordinarily low. Not zero, but low enough that in 200 to 400 billion star systems, it may have happened only once. The argument has critics. Many astrobiologists find it too geocentric, too focused on Earth's specific history as the template for what life requires. Evolution is creative. Life on Earth has found ways to survive in conditions that would have been considered impossible environments a few decades ago. Boiling hydrothermal vents, highly acidic lakes, the interior of nuclear reactors, the stratosphere. The requirements for life, defined broadly, may be far less specific than the rare Earth hypothesis suggests. And there is a deeper philosophical problem. We have exactly one example of the development of intelligent life. Exactly one. Drawing general conclusions from a sample size of one is not good science. It is, at best, informed speculation. But the silence is real. And the rare Earth hypothesis, for all its weaknesses, at least accounts for the silence without requiring anything terrible to happen, which is more than can be said for the next explanation. The second major class of explanation for the Fermi paradox does not argue that intelligent life is rare. It argues that intelligent life is common, or at least not astronomically rare, but that it does not survive. Something kills it. Not anything external, necessarily. Not a cosmic catastrophe that strikes from outside, though such things are possible. Something internal. Something that every technological civilization eventually does to itself or encounters within itself. A failure mode built into the nature of intelligence and technology that terminates the civilization before it can become visible to other civilizations. This explanation has several variants, and they share a common shape. Intelligence evolves because it is adaptive, because the ability to model the world, solve problems, cooperate in groups, and develop tools provides a survival advantage. But intelligence, once it develops, rapidly produces capabilities that outpace the wisdom required to manage them safely. The most obvious example is nuclear weapons. Humans developed the ability to split the atom and release nuclear energy in the early 1940s. Within a decade, multiple nations had weapons capable of ending civilization. Within 2 decades, the combined nuclear arsenal was large enough to kill every human being on Earth many times over. The Cold War brought the world to the brink of nuclear exchange on at least several documented occasions, including the Cuban Missile Crisis of 1962, when the world was, by the accounts of those involved, genuinely hours from a nuclear war that might have ended human civilization. It didn't happen, but it almost did. And the margin was not the result of superior wisdom or foresight. It was, in significant part, luck. The specific decisions of specific individuals on specific days. Vasily Arkhipov, the Soviet submarine officer who refused to authorize a nuclear torpedo launch during the Cuban Missile Crisis. Stanislav Petrov, the Soviet officer who decided not to report what appeared to be an incoming American nuclear missile launch in 1983, a decision that may have prevented a retaliatory strike. Individual human beings in individual moments making the call that prevented catastrophe. We are still here in part because of luck. If this is a general pattern, if every civilization that develops nuclear weapons gets 1 or 2 or a dozen moments where the outcome depends on a coin flip, then over enough civilizations the luck runs out for most of them. And nuclear weapons are just the beginning. The history of technology is a history of expanding capability. Each new capability is potentially double-edged, useful for building civilization, useful also for destroying it. Synthetic biology could cure every disease or engineer a pathogen that kills every human. Artificial intelligence could solve every scientific problem or be deployed in ways that end human autonomy and survival. Nanotechnology could build structures of extraordinary complexity or dismantle the biosphere. Climate change, driven by the same industrial capacity that built the modern world, is already destabilizing the systems that support complex life on Earth. The argument is not that any of these things will necessarily destroy human civilization. It is that each of them is a trial, a test, a moment or an extended period in which the civilization must successfully navigate a transition that its prior technological development has made dangerous. And the question the Fermi paradox raises in this framework is, how many trials can a civilization pass? If you are required to pass 1 trial to survive the nuclear age, and a 2nd trial to survive synthetic biology, and a 3rd to survive artificial intelligence, and if the probability of passing each trial is, say, 90%, then after 10 trials, the probability of surviving all of them is 35%. After 20 trials, 12%. After 30, 4%. Each individual trial seems manageable. The cumulative probability of passing all of them becomes vanishingly small over time. There is a name for the collection of threats that a technological civilization poses to itself: existential risk. The study of existential risk has become a serious academic field in recent decades, pursued at institutions like Oxford, Cambridge, and MIT, by researchers who apply the tools of probability theory and decision theory to questions about civilizational survival. The researchers in this field do not believe human extinction is inevitable, but they take it seriously. They argue that the probability of some form of catastrophic civilizational setback, if not extinction, then a permanent reduction in the complexity and capability of human society, is not negligible on the timescales of centuries and millennia. And if civilizations typically end within a few centuries to a few millennia of developing technological capability, if the window between capable of transmitting detectable signals and no longer in existence is only a few hundred years, then the probability of 2 civilizations being alive and detectable at the same time, even if many have existed over cosmic history, is extremely small. The universe might be full of ruins, dead civilizations, planets that once had cities and radio telescopes and the equivalent of our 21st century, that are now silent, the civilizations gone, the technology decayed, the electromagnetic signatures fading, the planets themselves continuing to orbit their stars in complete indifference to what they once contained. We would have no way of knowing. We cannot detect the ruins of a dead civilization at interstellar distances. We cannot see the remnants of cities that have been abandoned for 10,000 years. The only signature we can detect is the active one, signals being transmitted right now. And if no one is transmitting right now, if everyone who could has already fallen silent, we would see exactly what we see. An empty sky, not empty because no one was ever there, empty because no one survived. There is a third class of explanation that is less scientifically mainstream than the previous two, but that has been taken seriously by a number of researchers and that has received renewed attention in recent years. They are already here. Not here in the sense of living among us undetected. That is the territory of science fiction, not scientific hypothesis. But here in the sense of present in the solar system, or observable in astronomical data, or operating in ways that we have not correctly interpreted because we are not looking for the right signatures. The argument runs as follows. If a sufficiently advanced civilization wanted to observe a developing planet, to study an emerging technological species, to monitor a world that had recently begun producing radio signals, the optimal strategy might not be to make contact. It might be to watch, quietly, from a position that provides a good vantage point without intrusion. Where would you put an observatory if you wanted to watch the Earth without being detected and without expending enormous amounts of energy? The Lagrange points, positions in the Earth-Moon system, or the Earth-Sun system, where the gravitational forces balance and objects can remain stationary relative to Earth without constant expenditure of fuel, are obvious candidates. A probe at the Earth-Moon L4 or L5 points would be stable, have a clear view of Earth, and would be extremely difficult to detect because it would need to emit no signals and could be made arbitrarily small. Several researchers have proposed searching these regions specifically for artificial objects. The searches that have been conducted are limited in scope and sensitivity. More recently, the question of anomalous interstellar objects has introduced a new dimension to this discussion. In 2017, astronomers detected the first confirmed interstellar object to pass through the solar system, an object moving too fast to be gravitationally bound to the Sun, which had clearly originated from beyond our solar system. It was named Oumuamua, a Hawaiian word meaning first messenger or scout. Oumuamua was strange, not strange in a way that required any exotic explanation, but strange in ways that were sufficiently unusual to generate significant scientific discussion. It was unusually elongated. Its shape was estimated to have an aspect ratio of between 5:1 and 10:1, far more extreme than any naturally occurring solar system object. Its trajectory after it passed closest to the Sun showed an acceleration that could not be fully explained by the gravitational forces of the Sun and the planets. There appeared to be a small but measurable non-gravitational acceleration, as if something was pushing it. Various natural explanations were proposed. Outgassing, the release of gas from a comet-like object heated by the Sun, could produce a recoil effect, but no outgassing was observed. The surface appeared dry and inactive. Another explanation proposed that Oumuamua was an extremely thin sheet of hydrogen ice, accelerated by radiation pressure the way a solar sail is accelerated by solar wind. This would explain both the unusual shape and the anomalous acceleration. But the physical properties required, the thinness, the specific composition, would be extraordinary for a naturally occurring object. Harvard astronomer Avi Loeb caused significant controversy when he proposed that Oumuamua might be an artifact of extraterrestrial technology, a piece of equipment, perhaps a light sail from an interstellar probe, that had been drifting through the galaxy after being discarded by whoever made it. This is not Loeb's primary hypothesis. He considers it a possibility that should not be ruled out simply because it is uncomfortable. His argument is that if the only explanation for Oumuamua's anomalous properties is one that requires extremely unusual natural conditions, then an artificial origin should remain on the table as a hypothesis to be tested. The scientific community's response has been largely skeptical. The principle of parsimony, Occam's razor, suggests that natural explanations, however unusual, are preferable to artificial ones. We know natural, unusual objects exist. We have no confirmed examples of alien technology, but Loeb's broader point is worth sitting with. We might not be looking for the right things. We might be applying assumptions that alien technology would look like our technology, that it would communicate in ways we recognize, that its presence would be obvious rather than subtle, that cause us to overlook evidence that is present. The silence might not mean absence. It might mean we are not looking correctly. There is an explanation for the silence that is, in some ways, the most disturbing of all. Not because it implies that we are alone, or that civilization is doomed, but because it implies something about the nature of the universe that, if true, changes the meaning of the silence entirely. It is called the dark forest hypothesis. The name comes from a science fiction novel, The Dark Forest, the second book in Liu Cixin's three-body problem trilogy, but the underlying logic is a serious philosophical argument that has been discussed in astrobiology circles independent of the novel. The argument is this: the universe is a place of finite resources. Any civilization that survives long enough eventually needs more than its home planet can provide. More energy, more materials, more space. The logical response to resource scarcity is expansion. And in a universe where the distances between stars are measured in light years, where even the fastest conceivable spacecraft would take centuries to cross those distances, there is no possibility of coordination or negotiation between civilizations before one arrives at another's doorstep. In this environment, with long travel times, finite resources, and no possibility of real-time communication, the optimal strategy for any civilization that encounters another may be preemption. Eliminate the other civilization before it can become a threat, not out of malice, but out of logic. You cannot trust a civilization you don't know. You cannot communicate quickly enough to establish trust before the situation becomes dangerous. And the cost of being wrong, of extending trust to a civilization that turns out to be hostile, is extinction. The universe, under this logic, is a dark forest. Every civilization moves through it in silence, hiding its presence, because any signal is potentially a death sentence. Broadcasting your existence into the cosmos is like lighting a fire in a dark forest full of hunters. It tells everyone exactly where you are. The silence under the dark forest hypothesis is not the silence of an empty universe. It is the silence of a universe full of civilizations, all of them hiding, all of them listening, all of them terrified of being found. And if this is true, if the silence is the silence of concealment rather than absence, then what we have been doing for 70 years is deeply unwise. We have been shouting, not only receiving, we have been transmitting. In 1974, using the Arecibo telescope, scientists beamed a deliberate message toward the globular cluster M13, a tight group of about 300,000 stars, roughly 25,000 light-years from Earth. The message encoded information about human biology, our solar system, and our technology in a series of 1,679 binary digits. At the speed of light, it will not arrive at M13 for another 24,975 years. Other messages have followed. The cosmic call transmissions in 1999 and 2003, the teenage message in 2001, various other deliberate transmissions made by institutions and private individuals aimed at nearby stars. There is a serious debate in the SETI community about whether this is wise. Active SETI, intentionally transmitting signals that could reveal our existence and location to other civilizations, has been controversial since the practice began. Some researchers argue that the risks are manageable. If anyone capable of detecting our signals exists, they likely already know we are here from our unintentional radio leakage, which has been spreading into space since the early 20th century. The horse, as they put it, has already left the barn. Others disagree. The intensity of a deliberate, focused transmission is far greater than the background leakage of our unintentional signals. And if the dark forest hypothesis has any validity, if even a small probability exists that broadcasting is dangerous, then the expected cost of being detected may be so extreme that caution is justified. Stephen Hawking, in a 2010 documentary, argued explicitly for caution. He drew an analogy to the European arrival in the Americas, noting that contact between a technologically advanced civilization and a less advanced one has not historically been good for the less advanced one. He suggested that intelligent aliens might be nomadic, looking to conquer and colonize whatever worlds they found, and that advertising our presence to them was perhaps not in our best interests. The dark forest hypothesis cannot be confirmed or refuted. We don't know that the universe works this way. We don't know that civilizations are uniformly hostile, or that the logic of preemption is correct, or that there are civilizations out there capable of acting on it, even if the logic is sound. But as an explanation for the silence, it is at least logically coherent. And the fact that it is logically coherent is, by itself, quietly terrifying. If the silence means the universe is a dark forest, if every civilization is hiding because showing yourself is fatal, then the search for extraterrestrial intelligence is not a hopeful scientific project. It is a lottery, and the prize is extinction. There is a fifth explanation that sits apart from the others, not because it is more or less likely, but because it approaches the silence from a different direction, not asking what happened to other civilizations, but asking what we assume about them that might be wrong. The assumption underlying most SETI work is that an intelligent civilization, wherever it arises and whatever form it takes, will eventually produce detectable electromagnetic signals, radio waves, laser pulses, something that travels at the speed of light, something we know how to build and know how to detect. This assumption is based entirely on our own experience. We developed radio technology in the late 19th century. We used it to communicate across distances. We assumed that any civilization that passes through the equivalent stage of development would do the same. But consider where we are now relative to where we were 100 years ago. In 1920, radio communication was a novelty. In 2024, we carry devices that communicate via satellite across the entire planet, using frequencies and encoding schemes that a 1920 radio operator would not recognize as communication at all. We have shifted, in 100 years, from broadcasting powerful omnidirectional radio signals to using tightly directed, precisely encoded digital transmissions that leak almost nothing into the surrounding space. The electromagnetic signature of our civilization is, in some ways, already becoming harder to detect, not because we are communicating less, but because we are communicating more efficiently. Tightly focused signals, efficient encoding, minimal waste. A civilization with 1,000 years more development would be, in this trajectory, almost invisible to a civilization looking for the kind of wasteful omnidirectional broadcasting we produced in the 20th century. And that is assuming they are still using electromagnetic communication at all. A civilization 1,000,000 years more advanced than we are, and remember, this is a conservative estimate for what might exist if intelligence arose elsewhere, has had 1,000,000 years to develop communication technologies we cannot imagine. They might communicate using gravitational waves, ripples in space-time that carry information at the speed of light, but that our current detectors are barely sensitive enough to register from the most cataclysmic astrophysical events. They might use neutrinos, particles that pass through matter almost without interaction, detectable in principle but extremely difficult in practice. They might have technologies that use physics we haven't discovered yet. Or they might have abandoned physical communication entirely. Some researchers have proposed that the most likely fate of a technological civilization is what they call a technological singularity, a point at which artificial intelligence surpasses human intelligence and begins improving itself, leading to a rapid acceleration in capability that rapidly produces a form of intelligence so far beyond our current comprehension that communication with it would be like trying to communicate with an ant. If most technological civilizations rapidly transition to a post-biological existence, uploading consciousness into computational substrate, existing as software in machines rather than biology in bodies, then the physical footprint of those civilizations might shrink dramatically. They might migrate to environments that are more computationally efficient near cold objects, because computation is more efficient at low temperatures, or even to the far future of the universe when more total computation might be possible with the available energy. They might be invisible not because they are hiding and not because they are dead, but because they have become something so different from us that we would not recognize their presence even if it were all around us. The universe might be teeming with intelligence that has simply moved beyond the stage where it produces the kind of signals we know how to look for. If this is true, the silence is not informative in the way we have been treating it. The silence does not mean absence. It means our instruments and our assumptions are insufficient. We are looking for something, but we don't know what form it takes. And the thing we are looking for may have taken a form we cannot currently conceive. This is, in its own way, the most humbling of the explanations. Not frightening, not hopeless, just honest about the limits of a young civilization, barely 100 years into technological development, trying to understand a 13.8 billion-year-old universe. We may be like a 19th century naturalist trying to detect the internet. The signals are everywhere. We simply cannot see them yet. Step back from the individual explanations for a moment. Look at the full picture. We have 7 decades of listening and no signal. We have a solar system that has existed for 4.5 billion years with no confirmed evidence of alien visitation. We have a galaxy 100,000 light-years across, 12 billion years old, containing hundreds of billions of stars, and in all of that, no detectable sign of anyone else. And we have a list of explanations for why this might be, and not one of them is comfortable. The rare Earth explanation says we are extraordinarily lucky. Lucky in our star, our moon, our planet, our timing. Lucky in a way that makes us almost unique in the galaxy. The loneliness implied by this explanation is real and permanent. We are alone because we are an accident, and accidents like us don't happen often. The great filter explanation says something screens out civilizations. Either it's behind us, in which case we navigated something extraordinarily dangerous, something that almost no one else managed, or it's ahead of us, in which case whatever ends civilizations is in our future. The self-destruction explanation says intelligence carries within it the seeds of its own termination. That the same cognitive capacity that lets a species build radio telescopes also lets it build weapons capable of ending itself, and that most civilizations, most of the time, use the weapons before they master the wisdom. The dark forest explanation says the universe is full of civilizations that have learned that broadcasting is fatal, and the silence is the sound of an entire galaxy choosing to hide. And the transcendence explanation says that civilizations that survive their own development move beyond anything we can detect, leaving behind a silence that reflects not death but transformation. Each of these explanations accounts for the silence. None of them is cheerful. And here is what makes this genuinely hard to sit with. We cannot know which one is true. Not yet. Possibly not ever. The data we have, the silence itself, is consistent with all of them. The absence of a signal does not distinguish between a universe in which life is rare, a universe in which civilizations die, a universe in which civilizations hide, and a universe in which civilizations transcend. We are left with the silence as the only evidence, and the silence points in every direction at once. There is a phrase that philosopher David Brin uses: the great silence, the cosmic silence. Not just the absence of signals from SETI surveys, but the more profound absence of any sign of intelligence at any scale. No megastructures, no Dyson spheres, no signs of stellar engineering, no evidence of large-scale colonization of the galaxy, no inscriptions in the cosmos that say anything was here. The great silence is the universe's most persistent question mark. And the longer it persists, the more decades pass, the more stars are surveyed, the more sensitive our instruments become, the more thoroughly we examine the data and find nothing, the louder it becomes. The silence is not neutral. It grows. Each year of searching without result is a year in which the universe has continued to say nothing. The silence accumulates, presses, and somewhere in that accumulated silence, in 70 years of careful, dedicated, increasingly sensitive listening, is the answer to the most important question we have ever asked. We just can't hear it yet. Or we can, and it is not what we hoped for. There is something that happens when you sit with the Fermi paradox long enough. Not with the individual explanations, not with the rare Earth hypothesis or the great filter or the dark forest, but with the core of it, the simple, undeniable 70-year-old fact at the center of it. We are here. We are looking. We have been looking for a long time with increasingly powerful instruments, and we have found nothing. At first, this feels like a practical problem, a question of telescope sensitivity, of search strategy, of frequency coverage. something that better technology will eventually solve, a puzzle waiting for the right instrument. But the longer you sit with it, the longer you consider the full scope of the universe and the full scope of the silence, the less it feels like a practical problem and the more it feels like a statement. A statement about what the universe contains, or doesn't. Consider what it would mean if the rare Earth hypothesis is correct. If we are genuinely alone, if intelligent technological civilization has arisen only once in the observable universe, on a pale blue dot orbiting an unremarkable star in an outer arm of an ordinary spiral galaxy, then something extraordinary follows. Every question humanity has ever asked about the nature of the cosmos has been asked only here. Every piece of mathematics ever written has been written only here. Every piece of music ever composed, every story ever told, every act of love or cruelty or curiosity or creation, all of it happened here and nowhere else. The universe, in this scenario, did not produce minds to understand it anywhere else. Only here. The 13.8 billion years of cosmic history, the 2 trillion galaxies, the hundreds of sextillions of stars, all of it backdrop with only one small planet producing the consciousness needed to notice any of it. That is simultaneously the loneliest and the most meaningful possible picture of our situation. And consider what it would mean if the self-destruction hypothesis is correct. If civilizations arise throughout the galaxy, but none of them survive long enough to become detectable, because the combination of intelligence and technology is almost invariably lethal, then we are living in the moment just before our own trial. We are the civilization that has reached the dangerous threshold. We have the nuclear weapons and the engineered biology and the accelerating artificial intelligence and the climate crisis. We are, in the language of the hypothesis, the candles at the end of their wicks. Other candles have burned before us. They are gone. We don't know if we are different. We don't know if we have what it takes to navigate what they couldn't. We have no evidence either way. We just know that we are here now, and the transitions ahead of us are genuinely difficult, and the galaxy's silence is, at minimum, not encouraging. And consider what it would mean if the dark forest hypothesis is correct. If the silence is the sound of an entire galaxy in hiding, if every civilization that broadcasts is eventually silenced one way or another, then we are, at this moment, the loudest thing in the galaxy. 100 years of unintentional radio leakage, spreading outward in all directions. A growing sphere of electromagnetic noise announcing our existence to anyone within detection range. And a handful of deliberate transmissions aimed at specific targets doing the same more loudly. If the universe is a dark forest, we have been lighting fires, and we don't know if anyone is watching. Each of these scenarios is true to the silence. Each of them accounts for what we observe, and none of them, not one, leaves us in a comfortable position. The silence is the data, and the data does not deliver good news in any of the directions it points. But here is the thing that is easy to miss when you are deep in the logic of the Fermi paradox, working through the filters and the hypotheses and the implications. We are still here. Whatever the silence means, whatever the correct explanation turns out to be, we are still here right now asking the question. Still alive, still curious, still looking up at the sky with instruments we built ourselves and wondering what is out there. And that fact that we exist, that we are asking, is not nothing. It is perhaps the most remarkable thing in the observable universe. Come back to tonight. Come back to wherever you are. The room around you, the quiet, the dark outside, somewhere above you, above the ceiling, above the clouds, above the atmosphere. The sky is full of stars, hundreds of billions of them in the Milky Way, burning steadily in all directions. And in those stars' systems, planets, many of them, some in the right temperature range for liquid water. Some with the chemistry that, on at least one planet, led to something that looked up and asked, "Is anyone else out there?" We don't know the answer. After 70 years of searching, after every radio survey and optical survey and infrared survey, after every candidate signal investigated and every anomaly analyzed, we do not know the answer to the question. We are still, in the most fundamental sense, in the dark. And I want you to hold that for a moment. not as a failure, not as a limitation of science or a reason for despair, but as a fact about the specific moment in history that you exist in. You are alive at the exact moment in human history when we have become capable of asking this question with instruments powerful enough to get an answer, and when we have been asking long enough, carefully enough, to know that the answer is not obvious. 100 years ago, no one knew the universe contained anything beyond the Milky Way. The concept of other galaxies was controversial. The idea that we could detect radio signals from another civilization, that such a thing was even theoretically possible, was science fiction. Now we know the universe contains 2 trillion galaxies. We know planets are extraordinarily common. We know the chemistry of life is present throughout the cosmos. Amino acids have been detected in meteorites, in molecular clouds, in the interstellar medium. We know the universe had the ingredients for life almost from the beginning. And we know, because we have been listening carefully for 70 years, that we have not yet heard from anyone. What we do not know is what that silence means. It might mean we are alone. Genuinely, finally, completely alone, the only technological civilization in the observable universe, looking out at a cosmos full of stars and planets and chemistry, but devoid of anyone else who reached the threshold of consciousness and curiosity and the ability to wonder. If that is true, if we are alone, then we carry something extraordinary. Not just life, not just intelligence, but the universe's only capacity, in all its 13.8 billion years and all its 2 trillion galaxies, to know what it is, to observe itself, to ask questions about its own nature and trace the physics forward and backward in time and feel the full weight of existing in the middle of something enormous. If we are the only ones, then when we are gone, the universe goes back to being unobserved. The questions go unasked, the mathematics unwritten, the music unplayed. The stars continue burning, as they always have, in a silence that is now complete because the one thing that briefly interrupted it has ended. That is a weight worth feeling. Or maybe we are not alone. Maybe the silence is the silence of timing, civilizations separated by such enormous gaps of time and space that we have simply not yet found each other. Maybe the silence is the silence of technology. We are looking for the wrong signals, and the universe is full of voices we cannot yet hear. Maybe the silence is the silence of caution, other civilizations, wiser or more frightened than we are, keeping quiet and listening the way we should perhaps be doing. Maybe somewhere in the direction of the wow signal, something is there, not transmitting anymore, or transmitting on frequencies we haven't monitored at the right time, or waiting to see if we respond to what it sent in 1977. Maybe the 72 seconds of signal recorded on a summer night in Ohio were the most important 72 seconds in human history, and we spent the next 47 years failing to hear it again. We don't know, and that not knowing, that sustained, open, unresolved uncertainty about the most important question we have ever asked, is the condition you are in tonight. The condition all of us are in, not temporarily, pending the results of the next survey, but as a fundamental feature of our moment in history. We are the generation that is old enough to have asked and young enough to not yet have been answered. That is an extraordinary place to be. Think about what it means to be the ones doing the asking, not the ones who never wondered, who lived before telescopes, before radio, before the understanding that those points of light are suns, each one potentially with worlds. And not the ones who come after, who may know the answer, who may live in a universe where the silence has been broken or confirmed or explained in some way we cannot currently imagine. But us, now, in the middle, in the uncertainty, there is something about uncertainty that is easy to misread as emptiness. The absence of an answer feels like the absence of meaning. The silence feels like nothing, but the silence is not nothing. The silence is the universe's most persistent question, addressed to the one species in the observable cosmos, or the one among many we don't know, capable of understanding what is being asked. And we are sitting with it. Tonight, somewhere, a radio telescope is pointing at a star we have never visited, listening at a frequency chosen because a civilization capable of radio astronomy would recognize its significance, recording data that will be analyzed tomorrow by people who have dedicated their lives to the possibility that something is out there. Tonight, The sky above you contains the same stars it contained when humans first looked up and began to wonder. The same Milky Way, the same ancient light. And among those stars, somewhere, the answer to Fermi's question is hidden. We are alone or we are not. Something ended everything that came before us, or we are the first. The silence is concealment, or the silence is the truth. And we do not know. What we know is this: we are here. We are looking. We have not given up. 70 years of silence has not stopped the search. It has intensified it. The telescopes are larger. The computers are faster. The searches are more comprehensive. The people doing the work are as serious and as dedicated as they have ever been. Because the question is worth it. Because the answer, whatever it turns out to be, will be the most important thing humanity has ever learned. Because some questions are worth asking even when the silence is very long. Even when the sky gives nothing back. Even when you have been listening for 70 years and the only sound is the quiet hiss of background radiation from the beginning of the universe itself. The oldest sound there is, the afterglow of the Big Bang, filling your instruments, constant and undiscriminating, the sound of a universe that is telling you something, if you can only figure out what. Tonight, the sky is quiet. The telescopes are listening. And somewhere, in the direction of a constellation called Sagittarius, on a frequency close to the hydrogen line, the silence continues.